Hello all, I'm Naren from School of Chemical and Biotechnology, SASTRA. This is a short video lecture as part of the Chemical Engineering Thermodynamics 2 course. We are in lecture 16 part 3. In this lecture we are going to discuss about the reaction equilibrium constant Ka. Specifically, we will see how Ka can be related in terms of pressure and eventually how to capture the effect of pressure in equilibrium constant. In the previous lectures, what we have seen is actually the effect of temperature, how to capture the effect of temperature on the equilibrium. Now we saw that can be done in terms of the Van 't Hoff. Now this is specific with respect to the effect of pressure. Now let's go back to our definition of equilibrium constant, which we know it as K. So Ka is given as the product of the fugacity of the reacting species in that system. So this is fugacity of the species in the system to its pure component fugacity. But the pure component fugacity is evaluated at the standard state, and this is raised to their respective stoichiometric coefficient, right? This ratio of fugacity of the component in a solution system to its own pure component fugacity is what we call it as activity. So this is called activity of the component. So this actually measures how the component behaves in a system to a pure component. So it is a kind of the system behavior of a component. I would let me write like this. It is this is activity, and this activity actually behaves is a function of how the component I behaves in system in comparison with when it is a pure component, in comparison when it is independent, right, or having an individual existence. So suppose if you have a system with only that component and you compare that component in a reactive system, so how this fares with one another, that is measured by this ratio. So we can write the equilibrium constant as also Ai to the power of the stoichiometric coefficient. So this is the signed stoichiometric coefficient given by the reaction scheme. Now the only thing that has to be noticed that the reference can be at any temperature in generic, or in this case it is at the standard temperature. So this to denote that the reference is at standard temperature, which is typically 25 degrees Celsius. Now let's let us try to split this activity itself. So we will have to write this as Fi cap, which is the fugacity of the component in a solution to the fugacity of its pure component in the standard state. So that means if we think of a reactive system like AA plus BB giving Cc plus D times D, let's assume that the component, this is the first component, this is second component, this is third component, this is fourth component. So that means this is the stoichiometry of the first component, stoichiometry of the second component, stoichiometry of the third component, stoichiometry of the fourth component, and just the matter that the stoichiometry of the reactants are signed, so that should be minus A and minus B. If we have this, then that means A I to the power of stoichiometric coefficient for one single component, we can write it as Fi cap. This is Fi naught cap. Now if you are going to take a product of this, so for all the components A raised to the stoichiometric coefficient from I equal to 1 to n, in this case it's just 4, but in principle it can be any number of components and there can be more than one reaction also. Now this we can write it as a product of, we can split this product Fi cap to Fi cap naught the whole power this, which can be written as product of Fi cap raised to the stoichiometric coefficient divided by Fi naught raised to the stoichiometric coefficient. Now eventually this product rule can be split, so we can write it as this as Fi cap raised to the stoichiometric coefficient divided by a product of the pure component fugacity at standard state raised to the stoichiometric coefficient. Now this is what we get. So we have just split the product for the numerator, product rule for the numerator and for the denominator. Now what about the fugacity of a pure component and the fugacity of a component in a solution? So the fugacity of a component in a solution, fugacity of a component in a solution can be written as its fugacity coefficient times the fugacity of a component in a solution if it was going to be an ideal solution, or if it is going to be a vapor phase system. So that means we don't write it as ideal solution, then we compare this with the ideal gas. So that means here we are making an assumption that we are writing it for the gas phase reaction system. If it was going to be a vapor phase, liquid phase, reaction system, then we don't use fugacity coefficient. We use probably then the activity coefficient. Then one can write it as an activity coefficient, or one can write in terms of the ideal solution multiplied by how it compares with that. So that means, let me just write it. So this is the activity coefficient of the species times how the fugacity of that species will vary with respect to this. This is applicable in general to both vapor and liquid phase, whereas the top one in comparison is only with respect to the gas phase. Now let's focus on the first part. So we will just focus on the gas phase system, and this can be written then as phi I cap times the fugacity of a component in an ideal gas is nothing but its partial pressure. So we can write like this. So that means Fi cap for a gas phase system can be written like this. Similarly, if you talk about the fugacity of a pure component at its standard state, can be written as its fugacity coefficient. This is again a pure component fugacity coefficient times the fugacity of the pure component if it was an ideal gas. Here again I am restricting the discussion only to the gas phase system, and this is nothing but the pressure of the system, and obviously because it is at a standard state we just denote it by a standard state value. This. So now all we are going to do is to combine this expression and this expression has to be combined in this expression that we have got. So we are just going to combine these two expressions over here and then see what happens. Let me just write it in the next page. So we have fugacity of a component in a solution to be written as its fugacity coefficient times the partial pressure. Now remember, this is only applicable for the gas phase, and the pure component fugacity is also written as its fugacity coefficient times the pressure, but the pressure is the standard state pressure, which is typically 1 bar or 1 atmosphere. We are going to combine this with the expression that AI to be AI, the product of AI raised to the stoichiometric coefficient can be written as the product of fugacity coefficient in a reactive system raised to the stoichiometry divided by this is its pure component fugacity raised to its stoichiometry. So we are going to use this expression over here, and what we get is the product of this. Now there are two terms, so over here, so we can apply the product to both of this. So that means the product of partial pressure raised to their stoichiometric coefficient and divided by the product of for the denominator it is the pure component. It is, I would say that the reference pressure or the standard pressure raised to the stoichiometric coefficient times the product of the fugacity coefficient in a system, solution system or the reacting system raised to their stoichiometric coefficient divided by the product of fugacity of the pure component raised to their stoichiometric coefficient. If you see this part is entirely to capture the non-ideality of the component either in its pure component state or is it in their solution state. So we can write this term as K phi. Okay, this term denotes the respective partial pressure raised to their stoichiometric coefficient. So this is another equilibrium constant term which can write it as Kp, but here it is in terms of the partial pressure, that should be noted. And the reference pressure or the standard pressure is going to be the same for all the components. So eventually it is the same pressure but raised to their stoichiometric coefficient. So this is a third grouping that one can have, and this is nothing but the standard pressure, and if you just sum up all this stoichiometric coefficient, you end up in the delta n, which is the change in number of moles of the component during the reaction. So that means this entire expression can be written as K phi times Kp divided by P naught power delta n, right? And what you have here is actually Ka. So this gets you to the relation of Ka in terms of partial pressure. Ka is equal to K5 times Kp times the standard pressure times delta n, right? Now let's we can still decouple this. Now let's say, for example, what is Kp? Kp is the product of partial pressure raised to their stoichiometric coefficient, and we know that partial pressure is equal to mole fraction times the system pressure. So eventually this can be written as a product of mole fraction times the system pressure raised to their stoichiometric coefficient, which means this is split as yi raised to their stoichiometric coefficient times the product of pressure raised to their stoichiometric coefficient. So if the product of pressure raised to the stoichiometric coefficient eventually gives rise to P power delta n, and this is Ky, the equilibrium constant based on the mole fraction. So if you substitute this expression over here, we get it as K phi into Ky P power delta n divided by P naught power delta n. Remember, the numerator is the system pressure, that means it's a reaction pressure, whereas this is the reference or the standard state pressure. So now we come to the end of this video. To summarize, Ka can be written as K phi times Kp, which divided by the reference pressure raised to delta n, that is also given as K phi times Ky times P power delta n divided by P naught power delta n. So this gives a relation between the equilibrium constant and the pressure. This is the reaction pressure in the system, and the effect is based on the value of delta n. So we can have the cases, what if it is delta n is equal to 0, delta n greater than 0, and delta n less than 0, which so just to discuss this effect, so that means this is, there is no change in moles during reaction. Now here the mole increases in the reaction, so that means the product side there are more mole numbers than the reactant side, and delta n less than 0 is the moles decreases during the reaction, I mean in the course of reaction. Now delta n, just to recollect, is a summation of the stoichiometric coefficient, so that's what we write it as delta n. Now before we do this analysis, let us also make another quick assumption which is easier for us. Let us ignore the effect of non-idealities in the system. So that means let us say that k phi is 1. So that means we are not going to account for the non-ideality in the system for our brief case of discussion of this, and the standard state is like 1 bar, so eventually this denominator term will also go to 1. So if we make this assumption, we end up like Ka will be equal to Ky into p power delta n, right? So that means this is with an assumption that k phi is 1 and p naught is 1 bar. Now we know that Ka or ln Ka is minus delta Gr by Rt. So that means this is just a function of temperature in this case, because this is the Gibbs energy of the reaction. We have only accounted for the effect of temperature. So assuming that this is picked up only as a function of temperature, this is another assumption if you make. So that means given temperature, so given a reaction temperature, Ka is fixed, so Ka is a known value. So that means this side is going to be a function of temperature alone, and here you have the capture of pressure. So we need to capture the effect of pressure based on the product of these two terms. Now let's take the first case, which is a very simple case. What if delta n equal to 0? If delta n equal to 0, which means Ka is equal to Ky, so that means there is no effect of pressure, and this is fairly straightforward. Let's see the second case. If delta n greater than 0, if delta n greater than 0, so that eventually means p power greater n is equal to 0. So that means you have the pressure going to have a positive finite number. So this is for pressure greater than 1 bar. Obviously, if you do the reaction at 1 bar, then there is no effect of pressure. So this P is also greater than 1, or rather I would say is P is not equal to 1. Okay. So we can also have a vacuum pressure of 0.5, 0.6, suppose if for any specific reaction system. So if this is the case, and let us restrict this to higher pressures, because typically we do for higher pressure system. So that means I'm making that this for a higher pressure system, so that I can write like this, which eventually means that Ka is equal to Ky into p power delta n, and this number, if it is going to be greater than 0, which is typically the case for pressures higher than the atmospheric pressure, we are leaving out the cases, the specific cases where the reactive pressure could be at vacuum conditions, which is not typically the case in the industry. If that's the case, that means this is going to be only function of temperature, and we have said that the reaction temperature is already fixed, which means now Ky is equal to Ka power p power delta n. This being greater than 0, you will have Ky less than Ka. So that means with the increase in pressure, ky gets down. The equilibrium constant with respect to the mole fraction goes down with the increase in pressure greater than 1 atmosphere for the reactive systems where the delta n goes to is greater than 0. The third case is now then going to be the reverse, which you can easily expect. If delta n is less than 0, and again we are going to take the positive pressure systems greater than the atmospheric pressure. So in this case, Ka is equal to Ky P power delta n. So remember, delta n is less than 0. So in this case, Ky equal to Ka into P power delta n. Delta n is a negative number, so that means eventually in this case Ky will become greater than Ka. So that means if you increase the pressure, the equilibrium constant in terms of mole fractions increases if delta n is less than 0, and obviously the pressure is greater than the atmospheric pressure. So with this I will end this video. What we have seen in this video is a quick recollection of how to relate Ka as function of K5 equilibrium constant based on the partial pressure to the standard pressure raised to delta n, and this can also written as K5 Ky into P power delta n to P naught power delta n, where delta n is the summation of the stoichiometric coefficient. And we also see the effect of pressure on the equilibrium constant based on mole fraction. Thanks for watching this video.